Hey, welcome back. So we've seen how to insert nodes or elements into a heap. Now let's talk about the opposite, removing things. The standard place, the one area we usually remove from, is the root. So in a max binary heap, that means removing, well, it means the root in either case, but it means removing the maximum element, the highest value. And in a min binary heap, it means removing the lowest value, the minimum. So the method we define, we could call it remove. We could also call it extract maximum or extract max. And that's pretty common to see that. So when we go on to implement a priority queue, for example, where each element is assigned a priority level, and we want to remove things based off of their priority level, well, the highest priority in a max binary heap, at least, will always move up to the top. And so that's where we'll remove from in our priority queue. I can't speak. We'll always take that root out. It will be the highest priority item. Anyway, the way it works is similar to insert, where we can't just remove this and, well, we can't just leave it, of course. We have to have a new root. But then we can't just we could swap with any element and just put it there, but it's most likely going to be wrong. It's not going to be, the correct compact heap. So what we do is we remove this element and we swap it, or we put the current last value. This is a standard way of doing it. The last value, 12 in our case, would go here, and then we adjust, which I've always heard as sync or syncing down, but I was looking at Wikipedia. There are many terms for it. The procedure for deleting the root from the heap, effectively extracting the max element in a max heap or the minimum element in a min heap, and restoring the properties, so making sure everything is all kosher again, is called down heap, aka bubble down, percolate down, sift down, trickle down, heapify down, cascade down, and extract min and max. Nowhere did it actually say sync down, which is what I've always heard. So I was a little bit offended by that. They have so many options, but my life is a lie. There is no sync down. It's the same idea though, right? So we had bubble up, which was when we had an element at the end that is in the incorrect spot. It's the last item, and we bubble it up to the correct spot. Well, in this case, what we're going to do is put an element at the root that is most likely wrong and have it bubble down, sink down, sift down, trickle down, whatever, to the correct location. So for example, if this is what we start with, nothing's been removed yet, but if I want to remove the root, I call extract max is what our element or what our method is. It's going to take 41, remove it from this array or this list, and then take 12 and put it in place. So we end up with this. We remove 41 and 12 goes to the beginning. And so we end up with this structure, which is not a correct heap at all. So the next step is to then call whatever, sync down or sift down, and we compare it to its children. So we take 12 and we look at its two children. We take whichever one's larger, which 39 is, and then we're going to swap, assuming that 12 is indeed less than 39, meaning that 39 deserves or should be the new root more than 12. So if that's the case, which it is, we swap. Okay, so now that 39 is in the correct spot, we go back to 12 and we compare it to its new child, or both new children actually, and we're going to swap it with the larger one, if one of them is larger. If both of them are smaller, then we're in the correct spot and we don't need to swap. But in this case, both are larger. So we're going to swap 12 and 27. And we do just that, and we're done. 12 has now sunk down to its correct location, which is basically at the very end again. It's just that it used to be over here on the left because we had an extra node, but we removed that node, and so it had to sink its way down to the correct spot. But now everything is happy again in our binary heap. So let me show you one more slightly better animated example. On Visual Algo, they call it extract max. It's not called remove. But if I call it, step backwards, it removes that root, which is 70, and it's going to swap. Well, it's not actually a swap. It's going to replace it with the last element, 31. So 31 gets up there, and obviously that's wrong. It's not the largest element. It's not the max. So we compare it to the left and the right. And both of them are larger, but 67 is larger than 65, so we're going to swap there. Now 67 is the new root. It's the new maximum element. It's in its correct spot. It's cemented in. Now we do the same thing. We compare 31 to 45 and to 58. Both of those are larger. We're going to swap it with the larger one, which is 58. There we go. Now there are no children left. We have nothing to swap it with. And so it's in the correct spot. And then we would presumably return 70, which was what we removed, right? That's the whole point. We're removing the max and we probably want to return it. One more time, just for good measure, we'll go faster. This time, what was the element up top? 67. All right, we remove it, we replace it with 15. And now we compare. All right, 65 is largest, so now we swap there. Now we have 15 and 40 and 53. We swap with 53 because that's a larger one. And now it's at its final resting place. It doesn't go anywhere else. All right, so here's the pseudocode if you want to try and implement it. Write a method on our class, our max binary heap, called, you could call it remove, or I'm going to call it extract max or extract maximum. It doesn't take any arguments. You call it, and what it's going to do is just return the root, the old root, but also it's going to delete that root and update the tree, or technically the heap. So you can follow this pseudocode if you want. You don't have to do this line for line, but basically take the first value and swap it with the last one. Then remove that last one, use pop so that we get the old root. So we're going to have the root, swap it with the last item, and then pop the last item. But effectively, take the first item out and then replace it with the last item. Then you have to get to the sink down portion, this sift down, percolate down. Basically, start at the root index. Start at 0. Start with a little counter or an index variable, and find the index of the left child and the right child for that index. So for 0, it's easy, right? We know that if an element is at location 0, its first child is just location 1, and index 2 is the right child. But basically do this math, 2 times index plus 1, 2 times index plus 2. And take those two values that you find, the two children, then take those children and compare them to the element at the parent, the first element, the new root. And if one of them is larger, you're going to swap. However, take note that if both the left and the right children are larger than the parent, then swap with the largest child, as we saw over here. If I step backwards, when we swapped 15 up top, we compare it to 58 and 65. Both are larger, but you're going to swap with 65. And then after you swap, if you do swap, the child that you just swapped with, that index becomes the new parent index, and then you look for its new children and you repeat the process. You loop and keep swapping, loop and swap until neither child is larger than the element, which means that you've successfully sunk down that element that you put at the root. It needs to sift its way down to the correct spot. And then at the very end, return the old root. That's the whole point. That should be the maximum. So give this one a shot. Again, remember the math here. It's 2 times index plus 1, 2 times index plus 2 to find the left and right children given a parent index. Take that, find those children, compare both children to the element that is now at the root, and then swap if you need to. And then you now kind of shift your window over so that instead of looking at the root, you're looking at the new index and looking at its children, and you keep going until there's nothing to swap. All right. So give it a shot, extract max. I'll have a solution up next.